Good afternoon, everyone. My name is Haoran Li. So I'm from MIT Department of Civil and Environmental Engineering and MIT Sales Hub. So today I'm going to present a topic. I will collaborate with Miao Zhang, Hassam Adri Jeffrey, and Randa Perchin, which titled the development of Streamlined framework for probabilistic and comparative life cycle assessment of concrete pavements. So in this topic, we kind of have two phases. First, we develop the framework, and we then develop the tool, but then mainly focus on the framework, which is computational modeling we have done. So for this one, we started to evaluate the existing pavement LC tools or the methodology which has been developed in the past decade. So we were so excited to see that there's a lot of tools already existed or they're under development. We can see that there's many tools which they have do not include the use space, but they have quite a few data requirements that's shown in this table, which the plus means the quantitative identification of the data requirements. So these tools on the top of the figure of the tables, they require less data, but they can include the use space, which of the is the significant components of life cycle assessment of pavement. And there's also a few tools which they kind of include a few of these use space analysis, which is like the LICCER. They have been included a few consumption from the traffic, but obviously they need more data than these tools which they do not require the use space analysis. And on the bottom, you can see that there's many tools. They kind of include the PVI, which is the use space, the pavement vehicle interactions. So of these tools, they definitely need more data because they want to analyze the PVI impact of the pavement life cycle, especially use space. They have to evaluate the maintenance and rehabilitation effect. And also, the most sophisticated tool right now, which was developed by UIUC. So for them, they have developed this PLCA tool, which they include all the phases, all the components or sub-modulars of the use space, which are PVI, albedo, and carbonation. But obviously, this tool needs as many data as required from the users. If you are failed to provide them with sufficient data, they cannot give you an answer of the life cycle because they need a fully specified data as the input of this two PLC. So this comes to an idea like how can we implement the pavement LC, whether with less data, like 2+ in table, or some cases we have many data. We want to input data. So we kind of want to streamline this pavement LC framework. So we start to think from the bottom to up. So we want to see if we want to improve this pavement LC analysis, if we want to streamline this analysis, what we need to do. Definitely we want to include both embodied emission, which all the tools has included them. But we also need to include the use space emission because the use space emission seems more important than embodied emission for a long-term life cycle analysis. So in this case, for the embodied emission, we need to consider the material and the construction emission, which include the raw material supply, transportation, and energy production and fuel consumption from the transportation and from the construction on site. For the use space, we need to include all the use space sub-modules, which we include everything. So basically, pavement vehicle interaction for both deflection and roughness. We also include the relative forcing, which is also known as albedo, as well as the concrete combination. So to doing that, for the embodied emission, we need to provide the tool as the pavement material mixture design for mixture level life cycle analysis for embodied emission, for both concrete pavement and asphalt pavement. And also, we already noticed that the M&R, which is maintenance and rehabilitation, they are more than significant than the pavement design because their M&R itself, it is embodied emission, but it will significantly affect the long-term payment performance, which will significantly affect these use space submodules. So in this case, we want to know that for doing this whole framework, what we need for the data specification. So that is all the data we have been considered to develop this Streamlined tool, which we include the geographic location, climate conditions data, temperature, like the radiation, the raining days, moisture, etc., material properties. For example, the concrete like PCC elastic modulus rupture, and also for asphalt, AC banner tap, and also air content, etc. Pavement geometry, the length of the concrete pavement joint spacing, flat width, etc., and also for asphalt pavement, and most significantly the traffic loadings from the life cycle perspective. So to do that, we want to streamline this pavement LC as we saw in the previous table. So how do we do that? So we have been developed this so-called structured data and specification framework to streamline this pavement LC framework. So as we can see from the top, there's like a plus indicate the data requirements you need to provide it. So we want to adopt any data specification level from which is M1, less data, and until M4, which is more data with less under specification, but most specified data. So from level M1 to level M4, so the level M1 least specified data to the end of most specified data. So this table or figure shows the example of one of the input, which is called subgrid resilient modulus, which we can run, like say, for example, this has 200 data points, which can be 200 Monte Carlo simulations iteratively. And if we only have M1 data, which actually there's no specification of this data, which we just assume the user do not have the properties of their soil. So we just assume this soil can be any type of the soil, which has a large variations, can be from, let's say, 10 KSI to 50 KSI. But if the user has more knowledge, have more details of their subgrade, for example, this level 2, they know that it is self-clay material. So in this case, this variations of this level 2 data have been decreased within the range of about like 10 KSI to 40 KSI. Furthermore, if the user know more like under the M2 level, the categorical M3 has more shrinkage from the M2, which is clearly soil. In this case, the soil subgrade resilient modulus can be further reduced to a smaller range to less uncertainties. If the user have the detailed soil type, if they definitely know that it could be AASHTO 8-7-6 soil type, so furthermore, as indicated here, the level M4, the soil variations of the subgrade resilient modulus was further much more reduced and with much less variations. So in this case, this structured data identification framework can adopt any data uncertainty or data specification from M level 1 to M level 4. So here is an example of all the framework we have been seeing in the previous slides. So there's the different components. We need to know the traffic loadings, the material properties, and the pavement structure, geometry, and last is M&R scheduling. So for example, in the first M1 level, you do not have any clue of the material properties. We only know, or the user may only know that they are designing two pavement design alternatives, which is PCC and asphalt pavement. But they know that they will design this pavement for Arizona State. And they will know that they want to do one M&R scheduling within this, for example, 40 to 50 years analysis period, life cycle analysis. But they do not have the specification of what types of M&R they want to do and when they want to do this M&R. And the M2 level, they may know that they want to build a road for urban area, and they may know that this PCC is a standard grade concrete with a granular base and granular material as a subgrade. For the asphalt pavement, they know it is hot mix asphalt with the same base and subgrade half of the concrete pavement. And for the seminar, they may know that it is a minor repair, which for both concrete and asphalt. For concrete, it could be dam grinding, it could be some other minor repair. For asphalt pavement, it could be AC mill fill and other minor repair, but they do not know exactly when they want to do the seminar. For example, it could be the range from 28 years to 40 years. And for M3 level, they may, for the traffic system, they may know they want to build a urban minor arterial road. In this case, we have a smaller variations of these traffic loadings, for example, the AADT, etc., and traffic growth rate. And furthermore, for the material properties, they know it is M25 concrete with the AASHTO standard soils and south side subgrade. For the asphalt part, they want to do a high stiffness HMA surface layer. And for the MNR, for concrete, they want to do dam grinding and full depth repair, but they have no clue of the quantities of this dam grinding and full depth repair. And if they want to also do AC mill and fill for asphalt pavement, they know that they want to do some this MNR within 32 to 38 years, but they have no clue exactly when they want to, maybe 36, 37. But if they could provide the most detailed data specifications, for example, M4 level, they have a clear definition of their traffic loadings, and they have a clear definition of the compressive strength. For example, in this figure, it is 3,800 psi from concrete side, and different modulus, different resilience modulus for subgrade and base material. For the asphalt side, they may know that it is like elastic modulus of this asphalt is about 350 psi, and the same base and subgrade material. And for this case, they can provide the detailed quantities of this laminar with 100% dam grinding and 5% FDR for concrete pavement. And they want exactly do this dam grinding and FDR at the year of 35. And on the asphalt side, it is 3-inch AC mill and fill at the same time as the concrete side. So here we can provide all the results from level M1. So for example, it has a large variations of the life cycle GHG emission from year 1 to year 50. But when we are comparing like the full life cycle at the year of 50, which design has the least GHG emission? So the bottom figure shows that the JPCP with concrete has a 74% that is performed better than the asphalt regarding to the life cycle GHG emission. When it comes to level M2, so we can see that the variations of the life cycle GHG emission has been significantly reduced. When we comparing these two designs, the JPCP design has a 99% reliability that is better than the asphalt side. And when we are considering the M3, we now see a little bit reduced of the variations of life cycle GHG emission, but we have a 100% confidence level that JPCP is better than HMA. When we are considering M4, much smaller variations and necessities of this life cycle GHG emission, and we also have a 100% JPCP is confident that we are JPCP is better than HMA. But we're just a doubt that do we really need the M3 or M4 level of data specification? Because some users may not have that, but they still want to do that embodied image and use space. But for existing tool, they cannot do that, but now we can do that, so we know that if we just ask the user to provide the level M2, the decision makers or stakeholders can already make decisions with high level confidence that they only need to level M2 data, they can make a decision from the early design stage. So another thing we could do with this Streamlined pavement LC tool is to implement the life cycle GHG solution. So first, we also perform another analysis for Massachusetts. Right now, as a rural interstate, so we assume this is like AADT two direction, about 38,000 vehicles, and the truck percentage is about 20%, with the segment length is 1 mile. For the GPCB design, based on the Massachusetts DOT design guide and pavement output, we found the 10-inch PCC with 1.5-inch dot bar design and 6-inch aggregate and 12 feet width is the most common and can make the design under the threshold. And for the asphalt part, the 8-inch HMA, 8-inch aggregate base, and same slab width will also meet the threshold of the design performance. When we were considering the medium design comparisons, we can see that regarding to the RI performance over the life cycle, both pavement has a very good maintained RI prediction performance, with GPCB has 1 MNR and asphalt pavement has 2. And when we are considering the bar plot for life cycle GHG emission, the concrete pavement, which is design 1, is about 80% of life cycle GHG emission compared to the asphalt. So here is the comparative and probabilistic LC analysis. We have been seeing this result here, but for now I'm gonna propose another thing this tool can be done. So which we can see that the benefit time compared to the concrete to the asphalt is about 22 years. Which do we have any strategies to improve that or to accelerate that benefit time from 22 years to an early age? So in this case, first we propose improve the GPCB design. So we try 3 more design alternatives. So the GPCB BAU is the original design we have been proposed. And first we have to try to reduce the joint spacing of concrete pavement, which is GPCB, from 15 feet to 12 feet. And all the other design components keep the same. And the second one, we tried with the 12 feet joint spacing, we tried to reduce the PC thickness from 10-inch to 9-inch. And the last 12, except for joint spacing and PC thickness, we have increased the slab width from the 12 feet conventional line to 13 feet within line. So we have this result here. So from the GPCB GTS, we saw that there's a reduction of the GPCB BAU, and also the it's lower than GPCB GTS THK, which has a little higher life cycle distribution. But finally, we found that the final trail we have is like with 12 feet joint spacing, 9-inch PC thickness, and 13 feet slab width, which can reduce the original GPCP about 35% life cycle GHG emission. When we are comparing to our HMA's BAU, we found that there's a 50% reduction just because of the improvement of the GPCP design. And when we are considering this payback time, when we are comparing the GPCP one, originally 22 years, and now it was improved was shortened to 14 years. So another thing we have been tried is the GPCB MNR, which we have 4 trails. The original MNR for GPCB BAU was 100% diamond grinding with 5% at the year of 25. So the first trail we tried 4-inch bonded concrete overlay at the year of 20, and another 2 diamond grinding at the year of 30 and 40 respectively. Then we tried 6-inch bonded concrete overlay at the year of 20, and diamond grinding at the year of 35. So the last 2 trails, what we did is just to increase the frequencies of diamond grinding. The diamond grinding multiplied by 2, which is 2 diamond grinding at the year of 20 and 40 respectively. And the last is 3 diamond grinding at the year of 15, 30, and 40. So the results Okay, so the results show that there's some like up and downs, but finally we can reach about 5.9 kilodalton, which is like a 22% reduction from the original MNR scheduling. And compared to our like HMA BU, we can reduce 40%, which is not that impressive as compared to the improved GPCP design, but we can combine their schedule. But because of time of today, I don't have time to show the results. So regarding to the payback time, so we have seen that the original payback time was 22 years, and now it was reduced or shortened to 18 years. Okay, yeah, my first day was pretty short, right? I tried. So takeaways. The first is the structured data underspecification allows to statistically sound evaluation of competing payment design, even with less information. The second is the improve the GPCP design can reduce the life cycle GT emission by up to 35% compared to the original GPCP design, and by up to 50% compared to the HMA design alternatives, which the payback time was shortened from 22 years to 14 years. And the improved GPCP MNR scheduling, which can do is to reduce the life cycle GT emission by up to 22% compared to the original MNR scheduling, and up to 40% compared to the HMA design alternative. Regarding to the payback time, the GPCP, the improved MNR scheduling can shorten the payback time of GPCP from 22 years to 18 years. If you have any questions, you can ask now or you can email me because we ran out of time. So yeah, that's it. Thank you.